Hello everybody! The topic is on network analysis. So around us we are actually dealing with a lot of networks. Be for a road when you take your car to go from A to B, for instance. Sometimes we also use social networks such as Facebook, Twitter and others. We use the internet, and internet, there is a backbone for the internet, and so that is also a network. And other modes of transportation like an airline, we will talk about an airline network. So in order to go from A to B, I rely on a network, I rely on an origin and a destination. So generally all of these networks, right, that represent the infrastructure are simplified, and they are simplified by something that we call, an approach that we call graph theory. So we're going to try to represent this network by a set of nodes, okay, and a set of links, and links connecting those nodes. So I try to make an example here, relatively straightforward. I have a set of nodes here. They also call vertices, so this can be used interchangeably, although in GIS a node is not especially a vertex, just for the clarification, but in graph theory it is. And the lines that connect those nodes are called edges or links. Okay, so what is very interesting, of course, is to see the level of connectivity that exists at those different nodes. That something that we will talk about later on. So before we move on into things like shortest path or traveling salesman problem, we definitely want to spend a little bit of time talking about graph theory, things like diameter, things like degree nodes, and things of that nature, to build a solid foundation, and then we will move into the shortest path and traveling salesman problem. Okay, it may be interesting for us to look at the relationship between vertices and maximum number of edges in order to have what is called a maximally connected graph. So how do we get a maximally connected graph? Basically in a way that each vertex is connected to each other vertex in the graph. So as an example, I'm going to start very simple here. We have three vertices of three nodes. Those are in blue. In order to connect each node together, we're going to need three edges. Okay, if we had four vertices, 1, 2, 3, like the side of a square, we would need here 1, 2, 3, 4, 5, and 6. Now, one thing that is important, you will notice, is that I did not go like this, right? I hope you can see this one, because typically what happened here in a graph theory, when you have arcs or links or edges that are intersecting one another, then that would create a node here. Something that will go into the next example here. If we had 5 vertices, 1, 2, 3, 4, 5, then that would take us essentially 9 different edges in order to get a maximally connected graph, and so on and so forth. And so you can kind of see the pattern, right? And essentially you have, if you want to know how many edges that you would need, you would do 3 times v minus 2, and v, of course, the number of vertices. So you can check this out here. If we did 3 minus 2, that would be 1. 1 times 3, that's 3. Here we have 4, so 4 minus 2 is 2. 2 times 3 is 6. 5 minus 2 here is 3. 3 times 3 is 9. 6 minus 2, that is 4. 4 times 3 is 12. And so that is one way to see how many edges do you need to get a maximally connected network. Now, before we, of course, move into some of these interesting optimization applications such as the traveling salesman and shortest path, I'd like to spend a little bit more time to describe things like nodal degree or degree of a node, and other matrices that allow us to characterize the connectivity of a network. Okay, after having explained a little bit what a network is made out of, so simplified as a graph with vertices and edges, or nodes and links, however you want to call it, let's get a little bit into metrics that can characterize a network, right? One of them that we're going to talk about is a degree of a node, and we'll tell you how we go about this. But to simplify, what I have done here, I have created a made-up network, of course, with different nodes here that are blue dots, as you can see, and they are not numbered, but they are named A, B, C, D, all the way to I. Okay, and then we have links, right, or edges that connect those nodes. Not all of them are connected to all of the others, right? So that's quite interesting, because using this information of these links, we will be able to evaluate or document, if you want, the connectivity of each node to its immediate surrounding node. Okay, that is sort of called the non-stop connectivity. So if I just was willing to take, let's say in a flight, right, I'm just willing to take one flight from one place to another one, where can I go? And of course, if you are in the hub of an airline, then you can go many places. If you are in the spoke, so to speak, right, then that number is actually much lower. So in the GIS, in the Geographic Information System, there are many different spatial relationships, topological relationships, and one of them is connectivity. So based on a network like this one, it is possible to build this connectivity, right? And one way to do it, of course, is to go through a matrix. Here on the left-hand side, I have all the nodes, A through I, and here as well. And we are going to essentially assign a value of 1 for these entries if a link exists between two nodes. So let's start with A here. A is here. I know that I have a connection to B here that I can do non-stop. Here from A to C as well. So therefore we have B and C equal to 1. All the rest is 0, as you can see. From B I can go to A, I can go to C, and I can go to F. So from B I can go to A, I can go to C, and I can go through F. Okay, just let's look at another one from C. That's the one that seems to be well connected. I can go to A. Okay, I can go to B. So that one should have been, yes, from C I can go to B, sorry. From C I can go to D right here, and D. From C I can go to F. Okay, we have it here, and from C I can go to G, and I have it right here, and so on and so forth. One thing that I like to point, because this is the last one, is I. I is only connected to H. Okay, so I does not have a lot of connectivity there. It's kind of lost there. So if you were to sum up, right, for each row, you sum up the values. Here we have a value of 2. That's what the sum stands for, a value of 2. For B we have a value of 3. For C we have a value of 5. Okay. For D we have a value of 4, not bad. For E we have a value of 2. Okay. For F we have a value of 3. For G here we have a value of 3 as well. For H3 as well, and then we have a value of 1. So when I look into this, right, I can see that C, the node C, is the most, or the best, the most connected one, right? And this here, the sum, we are going to call this the degree of a node, the degree. Okay. Now this is quite important, because this type of metric is also used, let's say, in social networks or other type of network when we're trying to estimate what is the vulnerability. So if we were to remove one link, if we were to remove one node, what would actually happen to the entire network? Okay. So next I'd like to introduce a few more thoughts, or I guess a few more metrics, if you want, based on this matrix. And then we will go into other optimization problem. So one thing that I would like to add here is this accessibility matrix, right? This sort of connectivity matrix. This gives you, in fact, the non-stop connectivity, as I mentioned. But if you were to multiply this matrix with the same matrix, right, and to do that, right, you would take basically one column multiplied by one row. This is some sort of a matrix algebra. I won't get too much into that. You could get something called T2. Now, I've talked about the non-stop. That would be T1, right? That's kind of a matrix. T2, what does it mean? It essentially would, using this matrix, by multiplying them, it would actually find whether or not it's possible to connect, or to go from one location to another one, maybe by making a connection. So for instance, I can see that A is not directly connected to F, but if I make a connection in either C or if I make a connection in B, I can get to F, right? And In a way, this is not that complicated, but that's what maybe some airlines may be using. And it could be that you have one connectivity matrix, connection matrix here from maybe one airline and then another one, and you can say, okay, well, if I jump to another airline, maybe I can still go to that destination, right? So this is kind of how it would work. Again, this is a graph theory, and that's kind of how it works behind the scene. I'd like you to pay a little bit of attention to this network that I have drawn here. Now you know what the nodes are, you know what the links are. But it's important as we move forward to better understand where are the critical links, where are the critical nodes, something that we'll talk a little bit later in our class. Now, you know, this again could be, you can think about this as a social network, right? And there are ways to visualize social networks. There is a software called Pajek that can be used for that. But okay, so let's suppose that each node here represents an individual, right? And so you are here, you know, you have a social network, you have a few friends, right? And then you are connected to another social network. No, that could, for instance, well be, doesn't have to be on, you know, Facebook or Twitter, but that could also be a group. Let's say you have a group that plays let's say tennis here, and then you have also a group that studies geography and like maps. Okay, there is not actually that much connection. You happen to be one person that knows another one in another group, and that person has a lot of connection. Okay, now interestingly enough, if this links here disappears, right, then you have these two clusters that are not connected anymore. Likewise here, you may have one a cluster here, you may have another cluster here, and there is that one single person that is able to make that linkages. So if that person disappear, right, then these clusters are not connected. Doesn't mean that they are completely not connected. They still be connected via multiple steps, but there is not that direct link between those two networks. Or these two clusters rather. And you can see here there are different clusters. So for instance, if that link disappears, right, that cluster is kind of on its own. So I'd like, you know, this is kind of important to understand the role of a degree, but also go beyond that, like a 1-step, 2-step, 3-step, 4-step connections, right? So 4-step or a 3-step, why is it important? Because even if that link was to disappear, I can still go from here to here in 1-step, 2-step, 3-step, or 4-step. So it's possible to get there. Okay. So keep that in mind. Not so much for right now, but when we're starting to talk about network vulnerability, this will be a very important concept.